Um, there we go. Clicky. All right. So, 30 minutes we'll go through. I have the session recorded. I'll go through and post that recording, excuse me, as soon as I am able to kind of get that conversion thing ready to go. We'll go through, we'll take a look at some slides. F is for force, charge. D, talking about the distance between the charges and the force. And then we're going to add polarization to things today as a new thing. Part of the stuff that we'll be doing with the slides, we'll be going through and trying to review the Pivot Interactives lab that we started on Tuesday. I posted a message the other day also. A few of you commented or asked by email. I guess I don't have it here. A few of you, I must have done it just on the assignment page and the classwork page. But somebody asked about the points for your graph and your data table. I have to go back in and double check those and put the points in. The website cannot auto grade that. So I'll go back through it, and I hope to have that done today so you can see your actual full score on those things. Please know that if you see your score on those and you want to make a change and you try to change and it doesn't happen, there are a couple of buttons I can click that will allow you to make edits to those assignments. In Pivot Interactives, it's a little bit different, where I have to click on a couple of buttons to make sure an individual student can make a change after they've submitted it. So if you see something and you're like, oh, geez, I bombed that one, that sucks, I'd like to go through and fix that, send me a note and I'll double click the little dots and there you go. I will also try to, in the Pivot Interactives labs, on the parts where I am scoring things individually, like the data table and graph, or there are some other assignments also where I do some personal grading instead of computer auto grading. I try to put comments in those things so you can see where it was that we were just a little bit short and where we need to maybe make a couple of adjustments to get full credit, or at least what was missing, where there was a mistake. The same is true for some of the other assignments that you make or that you take in here. So far, we've been just doing Google Forms and Pivot Interactives and physicsclassroom.com stuff. Every now and again, we'll do an assignment that's like complete this Google Doc. And in those cases, I try to put comments in the actual document to kind of clarify the reason for missing some points and what might be helpful to get those things taken care of. So I intend to put feedback on all of those things that I individually grade. So if you're wondering what the bejeezers, why you lost some points, you should be able to find that. All right, so 4 minutes of babble, but I hope a useful babble for you. All right, so the Pivot Lab, things like that, I think we can get all of that in off of this slideshow. So I will do the present, and then I'm going to do the thing where you can ask anonymous questions again if you so choose. It's going to take me a second to click on a couple of things to make her get there. You can do it. I believe in you. You're a fantastic computer. We're getting there. Audience tools, start new. There we go. So let's see, I better, there. And then copy link. Okay, so I just put the link for the ability to ask anonymous questions in the chat for our Google Meet thing. So you should be able to click on that link, and if a question comes up, you can type in, click on the little make anonymous or ask anonymous thing, and it should go through. All right, here we go. Electric charges, distance between charges, force on charges, polarization. Whoops, a couple of quick fast ones. Again, I try to start off with a review just because sometimes it's been a little bit and we forget. So Hopefully we remember that electric charges produce electric fields, and those fields interact with other charges or with other things that produce electric fields. So that's the model that we've in physics have come to believe that creates the rule or that uses the rules that the universe follows. We know that charges can interact without touching. The thing that kind of permeates space, we've just named a field. And that thing, that field that interacts with them, through our testing, we've seen that it kind of behaves in certain ways, and we have these lines of fields that we can kind of study or analyze. Um, Electric fields only act on other objects that produce electric fields. Gravitational fields only act on other objects that create gravitational fields. So masses interact with masses through gravitational fields. Charges interact with charges through electric fields. Um, and we've looked at these things here a couple days ago, and we said, hey, we know of two types of charge that exist. And at some point we said, hey, we'll call some of them positive and we'll call some of them negative, the opposites. And it really actually was quite clever. Back in the day, the reason for going with positives and negatives is really because of a number line, right? It's possible to have 0 in the middle. And if I have +2 charges over here and I have 2 negative charges over here, well, if I have +2 and -2, when they add together, there's 0. And so it's like having no charge if you're some distance away. If we're a ways away and we see this two negative and this 2 positive, it's like there's, from a distance away, it seems like there's no charge there at all. If you're right in between the two, then there's stuff going on. But that's kind of why back in the day, hundreds of years ago, that's why they went with positive and negative for naming or the characteristic of charges. All right. Electrostatic forces. So if you have your note sheet, um, uh, this is one of those spots where you could write some things down. So electrostatic forces, that's a force that just happens between charges, right? If I have a positive and a negative charge or 2 positive charges, there's pushing and pulling going on there. We often call that an electrostatic force. There are other names for that too. Some people will call them Coulomb forces. The unit of measure for charge is measured in coulombs. But symbol is just a big old F, and unit of measure is newtons. But as we, in universally, the symbol for a force is F. When we start talking about electrostatic forces, we'll sometimes go with an E as a little superscript, like super above, to the left, say, hey, it's the electrostatic force of this charge on that charge. And if we break this word down, electro means we're dealing with charges. If something is static, we're saying that it doesn't change or move. So an electrostatic force is a force that deals with charges that do not move. Now, if we have a positive charge here and a positive charge here, they're going to try to push each other away. But if we're saying electrostatic forces, we're saying right here, what's the force on them? Later on, they might start moving. Maybe we're holding them in place right now. And if we're holding them in place right now, we can talk about the electrostatic force right there. If we let go and they start to move, well, we can still talk about this electrostatic force when they are at this position. And if they start to move, we can say, okay, now they're at this other position. What's the electrostatic force when they're at this position? It's possible to do those sorts of things. I'm not seeing any questions, so I'm going to keep on keeping on. Hopefully, when we were going through the Pivot Interactives, I forgot to change the title there, Force and Electric Charge Lab, hopefully we got some sort of a curve that looked like this. Now, not all of our dots are going to be like dead on the curve, the best fit line, the trend line, but our dots and the line tends to represent all of our dots. So the line is a really powerful thing. The line includes all of what's going on, where the dots are just individual trials. So this is kind of another way of thinking about trials. In middle school science, you were probably told, hey, never just one trial, you always have to do bunches of trials. Well, if we change the distance, each one of these is like a new trial. So that really helps give us a general feeling for things. And then we see as our distance increases, as our distance goes to the right on this graph, I'm going to change my mouse thingy so it's um, hopefully more, nope, I don't want that, I want that. So as our distance goes to the right, our distance is getting bigger, right? But as our distance goes to the right, we see the force gets smaller and smaller and smaller, right? The force, big values up here, small values down here. The force gets smaller as our distance gets bigger. And so if we say it like this with this equation thingamajig, oops, I intended to click to highlight. I forgot. Click advances the slide. My apologies. So if we look at it like this, if this number gets bigger, like if this number is 1, well, 1 over 1, square 1, 1 over 1 squared is still 1. The force is 1. But if this number gets bigger, and now if I double the distance to 2, well, now I have 1 over 2 squared, which is 1 over 4. And 1 over 4 is 0.25. So this force, when we doubled the distance, this force went from 1 all the way down to 0.25. So the force got much smaller. It didn't just go down by half from like 1 to 0.5. It went down to 1/4 of its initial value, 0.25. Another way of saying it is that we have this sort of relationship here where we have a over d squared. Force is equal to a over d squared. And the a really covers everything. We're saying that everything else is the same. We kept the amount of charge the same for this trial. The only thing that we changed was the distance. So this a would account for the amount of charge. That a would account for whatever is in the space in between those charges, if it's just air, if we suck all the air out and it's just a vacuum, if we put a piece of styrofoam in between, this A would account for all of those sorts of things. And I'm still not seeing questions, so I'm going to move on again. And then this is where we see actually what we have here is this relationship is really a Newton's third law deal. We have two different charges that are interacting. So if we say we have a positive and a negative charge, those two things are going to attract, right? And so if we look at the charge of the force that the left charge exerts on the right charge, shown here, the electrostatic force of the left on the right is A over d squared. Well, the electrostatic force of the right on the left is also A over d squared. And so from first semester, we said, hey, if it's the right thing on the left thing and the left thing on the right thing, then it's this thing hitting that thing hitting this thing. If it's just those two objects, no matter what, the force of the left on the right must be the same as the force of the right on the left. It just is. Their accelerations can be very different, but the forces must be the same size. So if we do this calculation, we know both the force this experiences and the force that other charge, the blue charge, experiences. I'm trying to highlight those on my screen. So if we know the force that this blue positive charge experiences, then we also know the force that this reddish negative charge experiences from each other. I hope that helps. Conductors, metals, positives still stay where they are. The negatives can move around. And that's when we get to polarization. Let's see. So we have two things that I would like to be able to do. Well, I guess a few things. Here, I'll show you this real quick. So let's see. We'll grab this. We'll see if this works. So just setting up a mini table thingamajigger here. You see that? Yeah, okay. Seems like it's sitting okay. And then where did my PVC? There it is. So what we end up starting to talk about with some of these things, I'm gonna go back a page. Okay, so, oops, 2 pages. So going back 1 page, conductors, positive protons stay in the nucleus, the negative charges can move. So this right now, if this pop can is overall neutral, All of the positives and negatives, there's a bajillion of them there, literally trillions and trillions and trillions of positive and negative charges there. Now the positives are going to kind of stay where they are, but with conductors, some of the electrons are kind of free to move. And so right now, if this thing is neutral, we got nothing, right? Now, if I charge this by friction, so that means I'm sanding electrons off of one insulator and onto another. So the PVC plastic is an insulator. The foam is also an electrical insulator. So I do this, and now I've got charges on, this is more positive than, either more positive or more negative. One way or another, this has a charge. The pop can is still neutral. Usually, we'll see if we can get this to work. Right? So what I'm doing there, let's say this thing is positive, just we'll pick one. If this is positive, then what I'm doing when I bring this PVC pipe near the can is I am pulling the electrons that are able to move. The electrons that are able to move on this go towards the positive thing, and they get attracted to the positive thing. So this is still neutral. But since some of the electrons can move, some of the electrons will go from here to be pulled towards this positive PVC pipe. And so it's overall neutral, but the charge distribution is not equal. Overall neutral, same number of positives and negatives, but the negatives can move. And when those negatives move, we say that it's polarized. So they can move to join to try to attach be attracted to the PVC pipe. In class, sometimes in the back, we would have like pop can polarization races where you can just find different things to see what's the best at getting a charge to make those pop cans move. So that's a thing I mentioned in the lesson plan today as something you can try. Something you can try if you'd like. Not mandatory, but an option. Sometimes, in these times, it's nice to have something different to do. Sometimes it's nice to mix it up.